Hi, thank you everyone. Thanks for coming out after lunch. So today I'm going to talk about challenges at 1.6T modules from a DSP perspective. I think you've seen a lot of people come today, talk about modules, talk about technologies. So I want to give you a different perspective. From a DSP supplier, what would we see the 1.6T, and have some comments towards that. So if you look at the technology and the market available, there's really three influences to building these modules. You've got the technology options. These are obvious. It's decisions whether they're CPO, pluggable, things whether you're copper or you're optical, decisions from the fiber type, several decisions from how many fibers, and even the technology, whether the lasers are EML, VCSELs. All these decisions play into how do you build this module. On the right-hand side is where we should actually start, is what does the end user actually need to build these modules? And there's several things that impact these decisions. Distance, the scale of data center. Not every data center is the same. Some are thousands of nodes, some are tens of thousands of servers. So big difference in the deployment and the model depending on the size of the application. But I think what we're hearing a lot of people talk about is the cost and power. So I'm going to address a couple of those applications and those effects on the modules. And then kind of the last thing, the elephant in the room, which people don't talk to, is there's really supplier influence. The investments and the competitive advantage they provide, that really drives a lot of the technology and the decisions in this market. So I'll address a couple of these, starting with the cost. This was an analysis done by a firm called Fabricated Knowledge. And what they're showing is the cost per bit, as you go down in the node shrinking of technology, we've reached a new era where previously everyone talks about Moore's law, the number of gates are doubling every generation. What they don't talk about is the actual cost of the products are actually increasing. So from 20 nanometer time frame on, the actual cost of chips has gone up over time. So when people say we're going to 7, we're going to 5, we're going to 3, you're actually saying you're willing to pay a premium on the cost of these chips. And also, we're talking about optical DSP products. For the optical DSPs, not only there's their digital content, but there's a significant portion of analog content. Even though we call these optical digital DSPs, they have front ends, CTLEs, they have ADCs. These are very much analog type circuits. And the analog circuits, as you go down in node and technology, does not shrink. So what that means is, as you keep going down in the nodes and technology, your cost is going up, and that's not a cost per unit. The other thing that's kind of missed is the mask cost. If you look today, 16 nanometer, you're looking at a $2 million mask cost. That's an upfront cost. As you go down, the prices are increasing from 7 million to 14 million. By the time we get to 3 nanometer, we're probably well over 20 million for a mask cost. If you take that into account of a cross product, typically, an IC company, you got to have margins that are 3 times your product costs. So if you take that $14 million, you multiply that by 3, you're talking about a $42 million recoup you have to do in the revenue. If you do that over 1 million units, your product cost is $42 more than someone else at a lower node. So these product costs really are, these mask and evolutions really affect the product costs going forward. And we hear a lot of people talk about, you know, let's go 5, let's go 3, and that makes a lot of sense for the power. But what you need to take into account is there is a cost penalty. So and the cost penalty is dollars to get that extra power advantage. One other comment on the DSPs is the maturity of the technology versus the process technology. A lot of vendors will race to the first node, you know, first to 5, first to 3. When you look at the design process, there's a big difference designing for a process that's brand new versus one that's in mature production. The first thing is the maturity of the silicon process models. They're still being developed by the fab in the early generations. There's lack of test chip data. So you don't have data of what the actual your circuits are versus the reality of the performance. And typically you're going to new circuit designs in these technologies. What all this means is you're going to have to over-design the product in the latest technologies. That's going to come at an area and a power penalty. In addition to that, you've got a higher probability of errata because everything's new. What that means is you're going to have increased firmware and an increased bring up time to solve all that. So those are things to be aware of. If you come with an IP that's been wrung out, it has test chips, you have empirical data for the performance, really what you can do in the next generation is you can optimize the power, you can optimize the area of these devices. What you'll actually also see is you'll know the application better. You can optimize and use what's called purpose-built DSPs that really focus on the performance needed for that application. And what this will do is it'll result in significantly less power and area for that device. And some of the things we've seen here, we have data showing products across generations. You can see at least a 33% power savings in the same process technology, and sometimes even more. So that's one thing that's overlooked. It's not only it's the process node, but it's how mature your DSP and your technology is in that process node. All these affect the product costs and the performance of the devices. Talking a little about some of the other parameters. Distance is a key parameter in the devices. And if you look at the distances that are less than 5 meters, you really have three options between the DACs, the AECs, and the AOCs. If you look at the DACs, as we approach the higher speeds, 112 and 224, the usability is diminishing significantly. You also see the gauge required for these speeds is affecting the weight, the density, the cost, and even the bend radius of these devices. Whereas in AOCs, you get that extra reach, but you also have the penalty of cost and power. So that's where the AECs are coming in with the kind of the Goldilocks position, just right between the cost and the performance of these devices. To get some real perspective on the AEC advantages here, I'd encourage you to look at some of the demos. On the left-hand side, there's a demo in the Credo booth for the AI and machine learning, and this really shows a device where if you didn't have these AEC cables on the sides at that density, you couldn't build that box. And over in the Experience Center, you'll see a 700 terabit router. This is one of the loudest routers that exist. You can see there from the number of cables, it would be next to impossible with other cabling techniques. Shifting a little bit more, if we talk about 224, the transition of 224 gig, what we see is historically looking at 10 gig to 112 gig. What we see is there's about a 50% picojoule per bit increase at one node. What that means is you need one more process node to make it equivalent. So have the 10 gig power at 112 gig, we needed to go to one more process down. So if we're at 28, we need to go to 16. So that's the general premise there. And when you look at the historical powers, the receiver would be 80% of the power, and the transmitter would be 20% of the power. So these are historical going forward from 100 to 50 gig to 112 gig PAM4 type devices. When we go to 224, one of the things we're seeing is on the receiver, because of the speed, the performance requirements, we're seeing about a 50% increase in the power required for the 224 over the 112 gig. And this would be in the same process node, apples to apples, just speed increases alone to meet the same performance of that technology. The difference though at 224 though is the receiver is not enough to fully equalize the channel. So now we're going to have to do more electrical circuits in the transmitter, do more pre-equalization in the transmitter to make this 224 gigabits per lane per work. What that does is that significantly increases the power on the transmit side. So what you're going to see is going from 112 to 224, we're expecting over 100% increase in the power to go from that speed increase. And that really translates to two technology nodes. So if you're doing a 7 nanometer device in 112, you got to go 2 down, maybe 3 nanometer in 224 to get the equivalent power in those devices. What this is telling you at the bottom here is 224 is going to require a lot more power per bit. And it goes back to that comments we made about the process technology, the cost, and the power. You're going to have to reach a real premium to get these 224 gig technologies versus the 100 gig technologies. Switching to another topic that comes up in this area is the coherent inside the data center. The coherent, widely used from data center to data center, but now we're talking about replacing the PAM4 with coherent technology. If you look at it from a DSP perspective, only the DSP IC, it's very manageable. We build direct-detect DSPs today. We can build a coherent DSP, similar cost, similar power in this generation. It's actually a lot of the other effects, though, that are impacting the coherent in the intra data center. The main impact right now is lack of interoperable standards. If you look at all the other module technologies, there's been standards that everyone could build to and design to. Today in the intra-coherent, all the designs that are being approached are more proprietary or specific to one hyperscaler. And that's going to be a significant impediment to the ecosystem as a whole for the coherent inside the data center. The other challenge for the coherent inside the data center is the direct detect, the 112 to 224, has a lot of momentum, has a lot of ecosystem. And so what you'll see is you'll see people going wider lanes, more lanes, or increasing that technology instead of switching to a new technology of coherent. The other disadvantage is a data center is typically fiber rich. It's not like an intra data center or between data centers where you have many long distance and fibers are expensive. Intra data center, you can move the fibers much more readily, add more as you need. The other thing is people are still innovating on direct detect, which is going to compete with the coherent also. Using multi-wavelengths or doing some muxing at the wavelength level coming from the direct detect signals will enable more bandwidth over fewer fibers in this market. So for 1.6T, you see a lot of viable technologies for the intra data center, whether 16 by 100, 16 by 100, you see several places where that exists today, and eventually 8 by 200, 8 by 200 will come in. Where the coherent inside the data center makes a lot of sense is when we get to 100 terabit switches, which is in the 3.2 time teraframe, 3.2 terabit time frame. In that time frame, we start to run out of lanes. So 4 and 8 lanes are needed for fibers. That's when it makes sense to move to coherent, so you don't have a lot of parallel fibers running all over the place in these devices. And then kind of the last one I'll talk about is the CPO versus pluggable. CPO, the real advantage is it shortens the distance between the switch and the fiber. And that has a lot of potential advantages, from reducing components, reducing power. The issue is there are a lot of technical issues to solve with this technology. From how the serviceability, from the longevity, just in general, to get the ecosystem in place. Today, most of the ecosystems for CPO are going to be closed. It's going to be a switch supplier generating everything all the way to the fiber. So it's a very closed ecosystem, very proprietary as far as the solution space goes for CPO. Whereas when you look at pluggables, you have multiple suppliers innovating many different ways. Pretty much on that first sheet when I showed all the technical possibilities, you have an optical module manufacturer using any one of those options in that technology. So you have multiple diverse solutions going forward. You're getting a lot of continuous improvements that are tweaks in this technology. So over time, the commercial terms and the technical improvements are continuous with these modules. What you also see is the CPOs, because it's such a closed system end to end, you're really designing it for one specific application, one specific distance. Whereas the pluggables, you can do whatever you want. You can do the same switch for 1 meter, 100 meters, or 10 kilometers. You can do very mix and match what you need for the fibers and the devices. So from that, the pluggable definitely is going to exist through 50T bit switches, and 100T is where we'll see that start to come in. One other topic is we talk about the laser or the transmitters. Several technologies here: VCSELs, DML, EML, SiPhos, and then most recently the thin film lithium niobate. All these are usable, and you can kind of go down the list here as far as the maturity and the existence. From a DSP supplier perspective, we can work with all these technologies. Our main issue on the DSP supplier is a lot of these have different drivers, different capabilities. Today, as you get the last few years, the SiPho was the big excitement. There's probably over 20 SiPho developers in the market right now. And what it did do is it took many years for that to get to production maturity. And you're starting to see that get to maturity at this point. From the DSP supplier, the challenge is every SiPho supplier has a different way of doing their interface, from voltages to currents to interfaces and number of lanes. So that's the challenge. The thin film lithium niobate is the most recent one. It has a lot of promise, a lot of higher bandwidth. The question will be how quickly it can get to production. So if that can get to production quickly, that will displace a lot of technologies, but that remains to be seen. So just kind of summarize on this. Some messages to leave here is AEC, optimal for the short interconnects. Encourage you to see the demos out there. The other thing I want you to realize too is when people talk about silicon technology, smallest is not always best. People say in their slides 5, 3, 2 nanometer. The reality is you got to start figuring in the cost and other issues with technology. And kind of the last point to that is there really is a trade-off. There's a trade-off between the lowest cost device versus the lowest power device, and those aren't necessarily the same technology or the same process. So that wraps up for me. So I encourage you to go see the AEC demos of both the Credo booth and the terabit router. And then our CEO of Credo is going to present next in the room night across in the hall over there. So I encourage people to go to that presentation also. Thank you.